Okay, this last video is going to be a little bit longer because you all understand what mixtures are for the most part, but what you haven't seen before are words like colloid, suspension, and Tyndall effect, or maybe you have seen them but you don't remember what they are. So let's start by looking at this third class of compounds called mixtures. And mixtures specifically are where we have different substances that come together, but they keep their own properties. So remember what I said about compounds. Compounds, when the elements bond together, they take on new properties. Well, that's not the case with mixtures. Mixtures, when they come together, are going to maintain the properties of the individual substances that make them up. Composition is going to vary, and most mixtures can be separated by physical means. And let's just go ahead. These are the two that you probably learned in 8th grade physical science. You've got homogeneous mixtures, and you've also got heterogeneous mixtures. Okay. And so right off the bat, for my people who are looking at the prefix here, we know that prefix homo means same, and we know that the prefix hetero means different. So even without remembering what those two terms mean, looking at the prefixes, you should be able to come up with some meanings. Homogeneous mixtures are the same throughout. And what I mean by that is that there is a uniform composition. And I'm going to give you some examples of that right now. I love to use food as an example because I love food, and it's a very uniform example. Think about peanut butter. Okay. If you looked at the ingredients in peanut butter, you're going to see several different things, including peanuts. There is a small amount of sugar, and there is oil. So all of these things get to combine together to make peanut butter. Now, if I were to open up a container of peanut butter, am I going to see these three things separated out? Hopefully not. Hopefully they're all mixed and they're uniform throughout. And so therefore peanut butter is a homogeneous mixture. The same thing with milk. If you look at the ingredient label, milk is made up of a lot of water and then several other compounds. But when you look at a gallon of milk, can you see all those different ingredients separated out? No. So milk would also be considered a homogeneous mixture. If you come over here and look at the prefix hetero, hetero is going to mean different composition. And the easiest and most universal example of this would be trail mix. Okay, trail mix is not uniform throughout. You could have different percentages of peanuts and raisins and M&Ms. It's different throughout. Same thing with a salad. Think about the lettuce, think about the cheese, the dressing, the tomatoes. I tend to tell students, think of heterogeneous mixtures as things that you personally could go through and physically separate a lot of times. Okay, not all the time, but a lot of times you could go through and physically separate those things out. So those are our two big types of mixtures. And what I'm going to do next is go through and be a little bit more specific with the homogeneous mixtures. This is where we're going to go and really break down the different types of homogeneous mixtures as well. And I cannot stress this to you enough. Keep in mind there's a lot of gray areas when it comes to interpreting what type of mixture we're looking at. So don't get upset if you're not sure about one. We'll talk through it and give ourselves some questions to ask. One of the key things on homogeneous mixtures, and probably the one that you remember back in 8th grade science, are solutions. Solutions are types of homogeneous mixtures. And solutions are where you have one substance, usually 90% of the time, we're going to call it water. And water is going to act as our solvent. And our solvent in a solution is what actually does the dissolving. And so again, most of the time when we're making up solutions this semester or even in life, we always use water as our solvent. And then the solute is what we put in to the water to be dissolved. So for example, I'm just going to use my favorite Kool-Aid. So we've got Kool-Aid powder, and then you've also got sugar. So if I was making a nice refreshing gallon of Kool-Aid today for my children, I would take the Kool-Aid powder and the sugar, which would be my solute, and I would dissolve it into the water, which is my solvent. So those are two terms that we need to know. And again, this would be considered a homogeneous solution because that Kool-Aid, if mixed up properly, is uniform throughout. It has the same composition throughout. You could go in and argue, well, if I put extra sugar in, then the sugar is going to settle at the bottom, and then it's not a solution. And we'll talk about that because, believe it or not, there are actually 3 types of solutions, and we'll get to that later on in the semester. We could also talk about coffee. In that situation, water, again, is our solvent, but for coffee, you've actually got the coffee grinds. If you add creamer or milk, that would be part of the solute. You could add some of vanilla syrup, that would be the solute. So key thing to remember is that your solvent is always going to be a higher percentage in your solution, and your solute is what is being dissolved, so it's always going to be a lower percentage within your solution. And that really goes over the 2 key parts, solute and solvent, that I wanted to talk to you all about with solutions. Okay, so we've talked about solutions, and another key thing to remember is the word dissolved. If you see something dissolved, that's another key word that it is a solution. Okay, now I'm kind of using the PowerPoint here to guide me. The next one that I wanted to look at, I'm actually going to go out of order here. Let's take a look at colloids. So when we're talking about solutions, if you were to look at a glass of Kool-Aid, you wouldn't be able to see anything. It would be almost like adding food coloring to water. You wouldn't be able to see any particles because they all dissolve, very, very small particle size. Colloids are a little bit different. Colloids, the particles are intermediate in size. So they're not terribly small, but they're not really big. These guys are called colloids, and colloids to me are the very hardest ones for students to understand because this is that gray area that I was just referring to. And so the best example I can give you is that if you're looking at the PowerPoint, take a look at slide number 14, where it talks about the Tyndall effect. Colloids display something called the Tyndall effect, and this is actually really cool, and you've probably seen this, especially if you're up early in the mornings out driving. The Tyndall effect is where colloids will actually scatter light. So if you were to shine light into a colloid, you would actually be able to see the particles suspended there. Think about your car lights. When you turn on your car and you drive out on a foggy morning, you can actually see the water particles suspended in the air. That's the Tyndall effect. And I'm going to show you this when we get back in school when we do our messing with mixtures lab. So colloids, these particles are intermediate in size. They're not small enough to be dissolved, but they're not big enough to be filtered out. Another good example would be ketchup. If you've ever seen ketchup, sometimes in real ketchup, I say, you can almost see the salt particles suspended within the tomato paste and vinegar mixture. I'm trying to think of more colloids. On slide 15, there's a really nice example showing you the scattered light. If you look at the red one, on the right-hand side, you can see that Tyndall effect and how that light gets scattered. Let's see. And again, colloids are homogeneous. However, there could be some situations where you could make a case that they're heterogeneous. So don't get hung up too much on that with colloids. The main thing I want you to associate with colloids is that Tyndall effect and that they're intermediate in size. And then the last type of mixture I'd like to talk to you about is a suspension. And this is probably the easiest one to understand because we said solutions have very small particles. Colloids are a little bit bigger. Suspension, the particle size is much bigger. Okay, when you think suspension, I want you to think snow globe. When you look at a snow globe and you see those white particles in there, if you were to possibly break that snow globe, could you filter out the water from those white particles? And the answer is yes. In a suspension, the particles are very large in size and definitely could be filtered out. Okay, so the particles are definitely visible. If you were to shine a light through them, it would be very obvious to you that you see these particles. They tend to settle out. Suspensions, if you were to leave a suspension sitting on the counter, the particles would settle out. So that would be another indication that you've got a suspension. And when we do that messing with mixtures lab, I'm going to show you that. You're actually going to make a mixture and have it sitting in a baggie. And when you leave the baggie at your desk, you're going to see those particles settle to the bottom. And then that would be an example of a suspension. The best chart that I could possibly show you all is if you're looking at the PowerPoint, slide 16 does a really nice job of kind of going through and categorizing each one of those Again, the suspensions are definitely heterogeneous, because remember what I said earlier about heterogeneous. Heterogeneous can be physically separated, and we just said that suspensions can be physically separated. As far as the colloids, I really want you to focus on those being the Tyndall effect and that they scatter light. They can't be separated by filtration. And then as far as if they're heterogeneous or homogeneous, that's such a hard decision to make. And so we'll kind of look at those individually when we do that lab. And the solutions, that's the one where the particles are very small in size. You cannot see them because they've been dissolved. If you have any more specific questions, definitely send me an email about these, but that's pretty much the three main characteristics that I was going to work through on those. If you're looking at the examples, the chicken noodle soup in the slide on slide 17 would obviously be heterogeneous because you can filter out the carrots from the noodles from the chicken. The next example was toothpaste. That would be a homogeneous mixture because, again, it's uniform throughout. When you look at those ingredients, baking soda, peroxide, things like that that are in toothpaste, they're all uniform throughout. And then, of course, the lemonade I used as an example earlier would be considered a solution. That sugar and that lemon juice has been dissolved into the water. I'm going to make one more video that kind of goes through and puts all this information together in one graphic organizer. So if you're still struggling, you might want to watch that last video.